Um, Thank you very much for the introduction. My name is Peter, and today I would like to talk about neural networks and the intriguing properties of those models. I choose this topic for the presentation because, first of all, it suits the it fits to the conference, to the profile of the conference. And it's also a very important topic because it shows us how vulnerable are the neural networks. And especially nowadays, when machine learning is applied to almost every product, no matter whether it's software or hardware, it is used so often. And and it is used because it achieves the state-of-the-art results in many different areas and in many different domains. This is important because people use this machine learning so often because it's so good, but it's really simple to, it's easy to forget about the really important factors like safety. And today I would like to show you some topics about the safety of neural networks. Some technical issues. So this is especially important if we think now about the modern applications of neural networks. If you think about autonomous cars, about the healthcare, when we use the machine learning for diagnosis, for the problems that where the machine learning is used to help doctors to diagnose patients and to analyze the patient's state. It is also used in the drug discovery and in many other areas. And actually, I could spend the whole presentation enumerating the number of applications that we can use, where we can use machine learning. But this is important because the neural networks, as I said at the beginning, have some vulnerabilities, and in such safety critical situations, we have to think about the safety critical systems. We have to think about the safety and those vulnerabilities. So a few years ago, it was discovered that the neural networks have the problems, and you can easily create the example of the input data and feed the network, which will finally result in the misclassification of that model. And this is called the adversarial examples. And let me ask the question, can you see the difference, can you spot the difference between those images? Probably, I think that most of you will say that no, these images are the same. And if I would ask you to classify those images, all of you would say that there's a panda on both images, and this is basically correct. But if you feed that images to the neural networks, even to the state-of-the-art neural networks, it can give you a totally different response. It classifies the left image as the panda and the right image, the image on the right-hand side, as a gibbon, which is a monkey. So it's totally different. And why such things happen? Because in fact, those images are not the same images. The image on the left side is the image that was used to train the neural network. It's original image from the dataset. But the image on the right side is original image plus some perturbation. Of course, this perturbation is scaled down, but you can see in the image that it's totally random. And this is causing the misclassification of neural networks. And this happens if you think about the classifier. When we train the classifier, it builds the decision boundaries. And you can think of these adversarial examples as the elements, as you can see on the left and on the right side, that live in a space near the boundary and are actually misclassified, so are very, very similar to the objects that belongs to the different classes. And people get interested in this area. You can see here the number of papers that was published about adversarial examples and related to the adversarial examples and adversarial training. And you can see that the number nowadays explodes, the number of published papers, because this is really important topic for the safety of neural networks. But before we start, let me ask you the question, or you can ask the question, should we even care about this topic, about these adversarial examples? And to answer that question, because not every model and not every application of machine learning needs to take care about these specific properties of neural networks. And to answer that question, we can ask ourselves about a few things: how the input is produced, who creates the input, how we can interact with the model, and whether the model is available in the external for the external environment. And we can propose the classification of those kinds of systems. The first one is an isolated environment. So imagine that you have a product, you've got the services, several services, and you've got some machine learning model, or specifically neural network. So the input to the neural network is produced by the services, and you exactly know what is the input and how it is created. And there is no chance that somebody will malform that input. And the same regarding the output of the network. So such system, we can think that we can say that it's safe, and we don't need to care about adversarial examples because there is no one can malform the input to the network. But on the other hand, we've got the non-isolated environments. And in these non-isolated environments, our system has similarly the neural network inside. Of course, it can have also services, but the main difference is that it interacts with the environment. Here we have the users that can provide the input and take the output from the network. So there's a risk that the user will malform the input and will try to hack or attack the neural network. It doesn't have to be the user. It can be just the external environment itself. So for example, if you think about the system that is detecting some objects, let's say camera, and it's actually taking the pictures of the environment, but somebody can change the state of that environment and indirectly malform the input to the network. Okay, technical difficulties. Okay, it seems to be working fine right now. Okay. So let's talk about the adversarial attacks. We can provide a classification for those types of attacks. The first classification can be whether the attack is the white box or black box. And you're probably familiar with that because these are the terms that are used widely in many areas in IT. And the second type of attacks are untargeted or versus targeted attacks. So let me briefly describe those attacks. White box attack, in white box attack, the user who is doing this attack has access to everything, has access to the model architecture, to the model parameters, and basically knows everything about the network. In the black box attack, user can only use the network to provide the input and to take the output. He doesn't know about the internal things in the network. And with a targeted attack, it's the easiest way to explain that is with the example. Here we have the classification task, and there's a picture of the car, and you can see that the classificator actually responds with the car with high confidence. With untargeted attack, the goal is to trick the machine learning model so that it misclassify. It didn't respond with the proper class. However, we don't care about the output. And there's a subtype, which is the confidence reduction. So we just want to reduce the confidence of the proper class. and the misclassification. So we just want to trick the network so it classifies it incorrectly. And the targeted attack, in the targeted attack, our goal is to trick the network so that it responds with the class that we actually want to. So we want to make the network think that here is the bottle, not the car. And to understand how we can create adversarial example, let me briefly refresh the knowledge how the network is trained. So usually we've got an image, which is the input data, and is provided with car, because we're doing this in a supervised manner. The input is fed into the network, and the output is produced. The output, which means the prediction, and the ground truth label is passed to the loss function, and the loss function gives us information how much different is the output of the network regarding the ground truth label. And then we're back propagating this information to the weights of the network, and we're providing the update. So the next time, the response of the network should be better. And we are doing this with gradient descent. So here you can see on the diagram the chart displaying the loss function, and the loss function is given in the first equation. So this is just the difference. You can think of this as a difference between the prediction and the ground truth labels. And we're providing the update by minimizing this loss. So we calculate the gradient of the loss function regarding the weights. And within each step, we minimize the loss function. So as you can see, the arrows from the bad predictions, we go down to the better predictions. So if you want to create the adversarial example and you want to trick the network so it is misclassifying something, we can reverse that process. So instead of using the gradient descent and minimizing the loss function, we can use that equations and goes up. So basically, we will, here in this equation, you can see that there's a change of the sign. So we are basically changing the parameters in a way that they are producing the worse and worse results. And to create the adversarial example with the fast gradient sign method, we are doing similarly. But this time, instead of applying the change to the weights of the network, we are applying this change to the input directly. So if you can take a look at this example once again, the weights are frozen, but during the backpropagation phase, we're updating the image itself. And of course, this update is scaled down so that the image and the adversarial image are actually, we can see the difference between them. For the targeted attack, instead of maximizing the loss function, we are doing something different. We are minimizing similarly as during the standard training, but with the different with a different label. So this time to the loss function we put the target label, so the one that we want to misclassify the classifier. Some technical problems. Okay. And we can extend that method in the iterative way. So instead of doing the one-shot update, we can iterate the process, of course, scaling it down, but this iteration will produce the better results in the fast gradient sign method. And there are also the other methods that I will not discuss today, and they work in a similar way. Sometimes they're optimizing different criteria, but they're also producing similar results. And here's another type of attack that I would like to present you. So this is the so-called one pixel attack. So instead of providing the update and malforming the whole image by some noise, this time we change only one pixel. And as you can see, this pixel is changed and is marked with the red circle. And you may ask if it's possible, because all these examples were done like the post-processing phase. So we applied these changes to the image that were directly fitted to the network. But what happened if we try to change something that in physical world? So researchers did some checks about this, and these are the results. On the left side, you can see the raw image that was used during the training period. And they printed that image and take a picture of that image. So the second image is this is not the adversarial example. This is the same image, but the picture of the image. And you can see that the classifier has some problems with classification. And on the right side, you have adversarial examples. I'm sure if you can see the difference between those images. But actually, the right one is a little bit more perturbated, so even human can see the difference between these images. But you can see we can successfully attack the neural networks in the physical world. And what about the black box attack? So probably the most interesting attacks, because if we create a product and we apply the machine learning there, we don't want to expose everything to the user. So in real world, the black box attack is something that is actually a threat to us. And the problem is that adversarial examples often transfer from the model to the other model. So it doesn't matter if you create your own model or your neural network and protect it, so you won't release for the public. Because somebody else can train another model, and adversarial examples that were created for that specific model can be transferred to your model. But if it not work, we can propose the framework in which you can create attack to the black box model. So we have a neural network, which is the black box, and we can call it Oracle. And what we are doing is that we're trying to get the data, fit the data to that network, and get the output. And based on that, we are creating our own data set, and then we're training the substitute model using that data set. And then we craft the adversarial examples on that network, and we applied it in a black box attack. And here are also the other propositions how we can enhance the attacks and make them more successful. So we can use the ensemble models, which was proposed by the researchers. So what they did is they get most top 5 state-of-the-art neural networks, and they try to train the 4 of them against one of them. And they repeated that process, so every time each network was tested. And actually, if you create a composed model, which is the ensemble model, and you apply the adversarial attack and adversarial examples that are crafted using that ensemble model, you can attack almost every other model, and with almost 100% accuracy. So this is the accuracy of the prediction, which means that the attack was totally successful if there's a 0. And here is the example from the same article. This is the example how people try to attack the real application. This is the Clarif AI, and you can feed the data, and you get the classification of those images. So as you can see, it's possible to attack even production-ready systems. Another interesting thing is that we can create something more. Not only add some noise to the images to fool the neural network, but we can create the so-called adversarial patch. The adversarial patch is created from the this exact adversarial patch is created from the ImageNet dataset, and it can be applied to almost every object. It can be even printed, and you can put that on the table as a sticker. So it will fool the real physical world images. And another important thing and the consideration that you should have take is that we can also do adversarial camouflage. So as you can see, the researchers tried to attack and the road signs. And to do that, instead of patches or standard adversarial examples, they tried to use the graffiti-like camouflage or art, let's say, and the attack, the targeted attack, was successful. So please imagine. I'm pretty sure that whenever you see some road signs, you can see that there is some graffiti on it or a sticker, and the same can be done with the neural networks, just by specifically preparing those stickers. And imagine that if you have a self-driving car and you can trick that in this way. This is terrifying. Another adversarial patch example, it is the paper released like 3 months ago. So students just created the patch which tricked the state-of-the-art YOLO network. This network is a state-of-the-art object detection system in real time. So having something like this image, this picture, you are invisible to this detector. And how we can defend against such models and such attacks. So basically, people tried a lot of things to defend against those adversarial attacks, and actually most of them failed. So we can even talk about the pipeline of failures. The first one was the dropout. The dropout is the technique to regularize the neural networks, and in this technique, what we're doing is during the training period, we are removing some of the neurons, even from the input. And we're training, we are doing the training step using only those neurons. And this, in the end, this helps us to avoid overfitting of the network. However, it occurs that it doesn't provide the defense against the adversarial examples. Another method was the weight decay, but it was the same situation as with the dropout. On the one hand side, if you provide a very big coefficient to the weight decay method, you could finally make the weights in the network so small that the model became robust to adversarial examples. However, the accuracy on the standard test dataset was pretty poor. So, in fact, in practice, we cannot use that method. Another proposition was the input transformations, and they also failed. Sometimes they were reducing the error rate of the adversarial images and attacks. However, if an attacker is aware of this defense method, it can defeat it easily. And the next thing is the adversarial training. So this is, let me talk a little bit more about it, because this is actually one of the methods that for the longer period of time was the state-of-the-art defense method for adversarial examples. And the idea is that having the original dataset, we can train the network and then produce the adversarial examples from this original dataset and extend this dataset to create a more powerful dataset that contains the adversarial examples and original dataset. And finally, we can fine-tune the network or train another network using this bigger dataset. And this provides some robust to the model. However, there are already known techniques to defeat that defense. So, but it's still in many papers you can find that this is still some method that you should use as a baseline. And the state-of-the-art method currently is the feature denoising. This is the method proposed this year on the CVPR conference, and they provide very simple thing to the network architecture. So somewhere in the middle of the network, for example, after some convolutional layers, we can put such filter. And what is happening here is that the data, the features produced by the nth layer goes to the denoising operation mechanism, and then is processed by the one-by-one convolution. And of course, we use the, and also we use here the shortcut connection, which helps to provide better results and to train bigger networks with bigger number of layers. And these denoising operations, maybe some filters. Authors of the paper proposed several different methods, and actually for this moment, this is probably the best way we can protect our network, so it's not attacked. And another important thing is that whether the adversarial examples are something that is that has to be used, that can be used and create that for images. And actually, researchers showed that it is possible to attack the speech-to-text systems. So you can create adversarial examples for the audio, and with audio, the situation is similar as with the images. So when we have the audio wave, we can create some noise, which is undetectable by people. But if we add this noise to the original audio wave, we can trick the neural network models. And the same applies to the text. And the adversarial example with the text looks like, but very similar. It's just replacing some words in a very specific manner. And another important question is whether this thing is specific to the neural networks or not. And research showed that we can apply and create the adversarial examples not only using machine learning models, but also the standard or the classical models that are used in machine learning. So, for example, you can create that with the logistic regression, the SVM, decision tree, and even with nearest neighbors classifier. And what is more interesting is that the adversarial examples created, for example, with the decision tree, can be used to attack neural network, and in the opposite side. So there's a question to you. So what do you think? Do the adversarial examples transfer to the humans? So if you can focus at the moment on the screen, I will try to do something, but I'm not sure if with the technical issues I will be able to do that. But let's see. Could you please tell me what you see? What did you see? Spider. Okay, so yeah, it is spider. Actually, I think that because of the lights here, it was hard to reproduce that result. But basically, this is the adversarial example that was tried on a human to attack the human perception. You can see that there's a lot of perturbations on the image, and this is very different from those things I discussed before. But the idea in the research was a little bit different. So that the researchers tried to test whether the adversarial examples, of course, if you look at this picture for a longer period of time, you will clearly see that there's a spider. But if you have limited time, like a fraction of the second, and you can see this perturbation, the different processes in your brain are working. So I think that there was an idea that you can compare that to the one shot of the neural network processing. During the testing, the result of this testing was that it's possible to transfer the adversarial examples to the to the people, basically. So we can even fool people. Okay, so that is the end of my presentation. Thank you very much. And if you have questions, I would like to ask you. I would like to answer them.
Okay, but before we go to the questions, I have one announcement, and I want to keep you focused for a moment, because one of you lost car keys, and if anyone found them, please leave them at the registration desk so that our unfortunate guest who lost them can pick them up. So thank you for your cooperation, and now we can go to the questions. So please run Slido on our screen. Okay, and our most voted question is from Dominic. What's the famous neural network attack and why it succeeded?
I think that there was many different attacks proposed. Actually, I showed you one to the Clarif AI, but there was also attack to the Google machine learning models, also with the success, and to the other giant tech companies. So I think at the moment this is the most famous attack. These are the most famous attacks.
Okay, Dominic, please remember to go here and pick up a book once you will be leaving the room. And let's go to the next question. In your opinion, what is the one best practice worth to be highlighted in neural networks testing? That's the question from Maciej Gruszka.
Mm-hmm. Okay, so I think that we should focus on the adversarial examples and testing robustness of our network against those examples, because it's not too hard to actually train the neural network that is providing you good results, but we also need to think about the robustness, and I would say that this is the most important thing, and this is what the researchers are now trying to do, to create the really robust networks.
Okay, let's go to the next one. Could we use neural network attacks as a tool for fighting with overteaching or as a way to escape network from local minimum? The question from Bartłomiej.
I think it's local minimum. Okay. Okay. It's a really hard question. Actually, I'm not pretty sure, and I will not provide you the direct answer for that problem. But at least partially, what the adversarial examples, when we used the adversarial examples in the training our model, this was called the adversarial training. We can actually, in some cases, increase the model accuracy. So so maybe this is some answer to that question, but this is not always the case.
So like the perfect answer, it depends. And I think we still have a time for 2 more questions, so let's go. What do you think about CAPTCHA images? Is AI ready to recognize it correctly, or it would rather make a mistake? Also from Dominic.
Okay, so to be honest, sometimes me myself had a problem with the recognizing the CAPTCHA correctly. So I think as long as we don't have a superhuman accuracy of the networks, it's gonna be hard. But so that would be my answer.
Yeah, the hated task to show all the traffic lights or all the buses from the Google. Yeah, that's the worst. Okay. And
you thought about this CAPTCHA? I was thinking about the older one.
But both of them are, I think, same hard. Okay, but one last question. How to hide from image recognition software?
Use adversarial patch. I show you the example how the guys from the Belgium University they created this patch that can be used. There's even a video available on the YouTube, So you can see that, yeah, I think that most of the image recognition softwares that are used in production are rather the real-time recognition systems. So probably they are not robust for the adversarial examples.
Okay, so now I want to hear a great applause for our speaker, Piotr Wawryka.
Thank you.